Alright folks, I want to look quickly at how you connect the servo to the CPE because it's a little different from how it's described in the textbook to connecting to the Arduino. I've got my little servo here, and my servo's got a brown, a red, and an orange wire. And so when I was looking at this, I wasn't entirely sure like which of those was the power, the ground, and the signal, and I didn't want to wire it up wrong. So what I did was I looked at the label on it, and it says Micro Servo 99 SG90. So I just threw that into Google, which led me to this data sheet for this little servo. And I can see right here, it says the orange is the PWM, the red is the VCC, and the brown is the ground. Great. So that's how I was able to connect this up. I've got the brown wire connected to a black alligator clip going to ground, the red wire connected to a red alligator clip going to my 3.3 volts, and then the orange signal wire connected to a yellow alligator clip going to A3 pin. In terms of the code is almost the same as what you saw in the textbook. We've got to include the servo library, include the circuit playground library. I have a servo variable type, and I'm naming that my servo. In my setup, I'm beginning the serial, I'm beginning the circuit playground library, and then I'm saying my servo, so that's this servo object, attach A3, which was that pin that I've got it connected to here. Oops. Here we go. That may or may not work. The pads are labeled A, 0 through A7, but those A values are really correspond to using those pins as analog inputs. Analog inputs. And the A0 one we've discussed is special because it can be used as an analog output for the speaker. The other pins, though, if we want to use them as outputs, it's really best if we use their digital pin values. But those aren't written on the CPE. It only says A3 there. So if I look at the Circuit Playground documentation from Adafruit and go down to the pinouts section, I can learn a lot more about these pads, right? And so if I look at the input and output pads, it's going to show me what each pin is. And if I look here, it's saying A3 is in fact shared with digital 10. Okay, so it can be a digital I/O or an analog input. It has PWM output, which is great because I need that for the servo. And it can also be a capacitive touch sensor. That's fine. But the important thing there was that this should actually probably be 10 if I want to use it as that digital output because I want the PWM. And you might notice this for if you try to do other PWM stuff like analog write to an LED or something else, you may need to use these digital pin numbers instead of the A pin numbers. The A pin numbers might work, but again, this is a potential bug that you could face. So I'm just going to say attach that to pin 10, which is the same as A3, and I'll make a comment there. Then I'm also saying pin mode 13, that's digital pin 13, which is the LED there, and that says D13 right on it, so I know that's 13 because I want to use that. And then my main code is just the two for loops that you saw from the text, going from 0 to 180 and then 180 back down to 0, writing that position to the servo with a slight delay. The other thing I want to do in my code, just to show you something else here, I want to turn on that LED, that D13 LED, when I push the D4 button. So I'm saying digital write pin 13, which is the LED, digital read pin 4. So when it's executed, it's actually going to do the digital read first and be like, okay, what's the value of this button? That's going to be 0 or 1, which is then going to write to that LED high or low based on whether it's 0 or 1. Okay. So I should also add in here pin mode for input, and this is one of the special ones where I can say pull down, so the default state will be 0. Okay. So the idea is that it's going to spin the servo back and forth, but then when I push this button, that LED will come on. Let's upload this and see what happens. Haha, it helps if I connect the power first, right? Uh-oh. An error has occurred. Let me check my board and my port. Yeah. There we go. Okay. So if we come back here, our servo's behaving as I'd expect it to, but then I push this button and the LED comes on, but now it's staying on, then it goes off. If I push this quickly, nothing, and then it happens, and then it goes off. What's going on here? It seems to be behaving really erratically. Well, the problem is that when this is doing its for loops, that delay in there, that 15 millisecond delay, adds up because we're doing it 180 times. So that's almost 3 seconds of delay in each of these loops. That's like 6 seconds of delay before I even get to this check here. This check, by the way, is similar to me saying like if digital read for equals 1, you know, write the LED, else turn it off. So that's really problematic. If this has to do with like threading and multitasking. The Arduino chips are single process, single thread chips. They can't actually multitask. They do the code one line at a time, and when you're delaying, it's basically asleep and not responding to anything. So I need to figure out a way to be able to do this in such a way that I can still read my pin really quickly. Okay, so let me disconnect this because it's kind of irritating for a second, and I'm going to show you 2 ways that you can deal with that. Let me get rid of that one. And so here's my second demo, and this is a lot of this is gonna look very similar. I've got the libraries, my servo. I have 2 new variables: position equals 0 and increment equals 1. My setup is gonna otherwise be the same. I'm gonna add that pin mode that I forgot in there for pin 4, which is gonna be an input pull down. And now in my loop though is very different. And it looks actually a little cleaner. So I'm gonna start out by saying if my position equals 0, I want my incrementer to equal 1, right? Like I have up here as the default state. However, if my position equals 180, I want my incrementer to equal -1. I am then going to write my servo position here. And instead of using a for loop to increment the position, I'm going to have this line, pause plus equals the incrementer. So this is saying, every time this loops, take my position variable and add the incrementer to it. So when I'm going up, it's going to be 0, 1, 2, 3, 4, etc. When I hit 180 though, my incrementer is going to switch to being a negative number. So I'm still adding my incrementer here, but if so position is 180, it's going to add -1. So it's really going to subtract 1. So then I'll be at 179, 178, 177, etc. As we go back down to 0, my incrementer switches to being positive again, and it goes back up. I still have the delay in here, the 15 millisecond delay, and then this is the same. So if we try this, we can see our servo behaving just the same as it did previously, but now our button is very responsive to clicking while the servo is going. That's pretty neat. I like that. This delay, though, could still get in our way, especially if we were dealing, for some reason, with a longer delay, like 150 or 1,000. That would we'd still have the same problem. And just to show you that, I will upload this. This will cause our servo to also turn slower, and I push the button, and sometimes it happens and sometimes it doesn't. That's irritating, but that's because the delay is too long. So with this 15 millisecond delay, this code's probably fine, right? Like that's too fast for a human to notice. But let's say it wasn't, and we really wanted to completely eliminate delays from our code so that this loop was running constantly, right? And just to reiterate here, the difference between these two, right? This one is running this loop every, slightly more than 15 milliseconds because it does take some time to process these lines. But basically every 15 milliseconds, this loop is going to run. Whereas this loop is only going to run like once every 6 seconds or so because we've got almost 3 seconds of delay here and almost 3 seconds of delay here. So we're only going to do this check once every 6 seconds versus once every 15 milliseconds. So this is significantly faster. But let's look at one more way to deal with this. And here I've got, sorry, let me disconnect that. Version 3 of the server code. And this is a reasonably intermediate or advanced technique, but you will see this a lot if you start looking at other folks' code, so I want you to be aware of it. Again, same libraries, same initiation, except now I've got a timer variable as well. My setup is the same, and I keep forgetting that part. What am I doing? There we go. Now in my loop, where this is slightly more complicated, so I don't have the delay. The delay's gone, so there is no delay on running this line. So this is going to check like every millisecond, which is great. What I'm doing is this, all of this, in terms of incrementing my servo, is the same, right? If position equals 0, make it incrementer 1. If it's 180, make it -1, write the position, and then plus equals the increment. That's all the same. So the only thing that's different is this conditional that I've put this stuff within. And so I'm saying if millis is a custom function built into Arduino, and it returns the number of milliseconds that have elapsed since the Arduino or Circuit Playground was turned on. So it gets powered up, and this millis is like a counter, and it's counting the elapsed time that has gone by since you turned it on. And so that's going to give me an integer number. I'm going to check if that is greater than my timer plus 15. This 15 I'm getting from that delay that I used in the previous sketch, right? So that's the millisecond delay I want. Timer is my variable here. So when I initialize the sketch, it's 0. But then as I go through, every time this validates and runs, I'm going to reset my timer to equal millis. So let's think through this, right? So I initially turn on my sketch. Timer is 0. We get to the loop. I say if millis. It reads, checks millis. Millis equals, let's say it's been 10. To run through the setup, it takes 10 milliseconds. Or actually, it will be 1,000, right? So it's 1,000 from my setup. 1,000. Is that greater than 0 plus 15? Yes. So it's going to do this. So it's going to do my checks, write my servo, etc. Then it's going to say timer equals millis. So now timer equals, it's going to equal like 1,001 or something, right? Because this does take time to process. Okay, so timer equals 1,001. It does this check. We come back through, and we're back into the loop. And if millis, so it's going to check millis again. And millis reads in at like 1,003. Is 1,003 greater than my timer, which is 1,001 plus 15? No, it's not. So it's going to skip that. And it's going to do this check. And it's going to come back. And we say, if millis, so now millis is 1,004. Is that greater than my timer, which is still 1,001 plus 15? No, it's going to go and check. And so it's going to keep looping very fast until millis, we get millis back. Millis equals 1,017. Is that greater than my timer, 1,001 plus 15, so a total of 1,016? Yes, it is greater. Then it's going to increment this again. Okay, so we're introducing a delay here with timer and millis that will not block the other code at all. So let me upload this and show you. Let me try again. All right, our servo is doing the same behavior. Our button why is that happening? LED's on. Ha! Because I'm set input pull up. I want input pull down. Okay. Now our button works as I would expect it to, and it's very fast, right? So there you go. The one danger of using millis is that as a timer, it counts up forever, from when you power this on. So when you power this off and plug it back in, millis resets to 0. That's fine. At a certain point, though, the variable space allotted to millis will run out, and millis will reset itself to 0 at some point. And if we look this up in the reference, and it's going to give us this note, right? It's an unsigned long. Logic values may occur if you try to use smaller data types. And it doesn't say right in here about that, so let's look at if we can find that unsigned long data type here. So won't store negative numbers, so unsigned long can be from 0 to 4 billion, 294 million, etc., etc. a huge number. But that's how many milliseconds it will take before this resets, because when it gets to, blah, 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 296, it can't store that value. It goes back to 0 and starts from the beginning again. But if we take that and we divide that by 1,000, that's how many seconds we have. That's how many minutes we have. That's how many hours we have. That's how many days we have. So after 49.7 days, this is going to reset. So if we're making something that's going to be like a long-term installation, and we're using millis to do this timing, we do want to be cognizant of that. But that's a very kind of like unique fringe case, that it can happen, and it is something to be aware of. So there we go. There's 3 different ways of looking at how to use the servo with the Circuit Playground Express, and how to avoid problems with delays blocking other aspects of your code from running.